This is 40 Days of Chemistry, Part 15. This time we're looking at the second part of 9.2.1. It's a focus on addition polymerization. So what is addition polymerization? It's a polymerization that proceeds by addition reactions between monomers that have a double bond to form the addition polymer and no other product. And it happens in 3 stages. And the first of these stages is initiation. And this is where some chemical, it could be an initiator or a catalyst, reacts with the double bond of one of the monomers, therefore breaking that double bond. And by breaking the double bond, one of the electrons from the double bond ends up in a bond with either the initiator or the catalyst. 2 electrons remain in the bond, which means there's 1 electron free at the end of the molecule which is unpaired. Therefore this growing chain is called an activated chain. It's got an unpaired electron. It's also called a free radical. That means it's very reactive because electrons like to be in pairs. They like to form covalent bonds to be in those pairs. And that leads straight to propagation. This is when the activated monomer or the activated chain reacts with the double bond of an adjacent monomer. So here we have in the diagram that free radical electron, that unpaired electron, reacts with the double bond of the adjacent monomer. And by doing so, it forms a single bond, and that single bond is here. 2 electrons remain in that single bond from that next monomer, and now the activated chain, or the end of the activated chain, or the free electron, unpaired electron, is right at the end of the chain again. And that process can continue and continue and continue, and that's the propagation stage. The propagation stage finishes with termination. This is when 2 activated chains, so these 2 chains here both have an unpaired electron at the ends. When they meet, those 2 unpaired electrons can form a single bond, and there is that single bond there. And now the chain is complete. All electrons have partners, every electron's in a bond, and the chain stops propagating because there's no more activated chain. And this is the termination step. Now, polymerization is quite a chaotic process. Chains of different lengths, as we've shown here, collide, combine, and react to terminate the process, and therefore there's a distribution of chain lengths produced in any polymer. And the molecular weight of a polymer, because it's just not one molecular weight, there's a whole range of molecular weights, the molecular weight of a polymer is reported as the average molecular weight of the polymer. And this little sketch shows you how many chains you have for each molecular weight. You've got a very few amount of chains with a very small molecular weight. Some chains have a very high molecular weight, but most chains have this average molecular weight for the polymer, and that's what's reported for molecular weights of polymers, because they are a mixture of different chain lengths in a polymer sample. And one of the things to look at first is LDPE production. And what is LDPE? Well, LDPE, or polyethylene, low density polyethylene. Polyethylene is the addition polymer of ethylene monomers, and there's a reaction there. You've got N ethylene monomers, or in this case 2N ethylene monomers, reacting together to form this chain here. This chain can go on and on and on for N units, and that is the polyethylene chain. And what happens in production of LDPE, particularly low density polyethylene, is the chemical we use to initiate the reaction is an organic peroxide. And it's not a catalyst, it actually reacts with the monomer and stays reactive with the monomer, and therefore that organic peroxide remains at the end of the chain. Because this process is activated by the initiator, that means the end of the chain, the propagating chain, is free to loop back around. As we can see here, the chain is looping back around in itself, and there is that free unpaired electron looping back. And what can actually happen is, where that free electron is, it can actually attack one of the bonds holding one of the hydrogens on from a previous carbon, and that hydrogen can actually leave this carbon here and join on to the end carbon, making a single bond at the end carbon. What that leaves, of course, is the fact that there is the unpaired electron now halfway along the chain, and therefore when the next monomer comes along to react with the chain, it's going to react to that side of that unpaired electron, and therefore going to have a branch growing off the side of that particular polymer chain. And therefore low density polyethylene, we get branch polymer chains, and then because there's branch polymer chains, the chains can't pack closely together, hence being low density. Next we have HDPE production. We use a Ziegler-Natta or a metallocene catalyst, which is used to initiate the reaction. Because it's a catalyst, it is not consumed in the reaction, and it is not part of the polymer chain, it gets reformed at the end. And because we use these for HDPE, we get long unbranched chains, and that's because the reaction happens at the interface of the catalyst. As you can see here, here is our propagating chain, but the free radical, or the free electron, is there. The free radical is always trapped at the surface of the catalyst. So even if this end does move around, there's no unpaired electron here to actually cause backbiting. And every time a new monomer comes along, it reacts at the side of this free radical, the chain gets pushed along one more unit, and the reaction keeps taking place at the surface of the catalyst, therefore getting long unbranched chains. Because they're long and unbranched, that means they can fold over each other quite closely and form these nice crystalline type patterns, and therefore we've got very high density packing, hence high density polyethylene. So what are they used for? Well, they've got some properties in common. They're both covalent molecular polymers, therefore they're both electrical insulators. They're water and chemical resistant, and they're tough, which means they're fracture resistant. But because of the unbranched chains, H2PA is close packing, it's got high density, it's got strong interchain bonding, giving it a high melting point, boiling point, hardness and rigidity, and it's also opaque. And therefore it's used for outdoor furniture because of its hardness and rigidity. It's used for appliance casings because it's electrical and chemical resistant and also quite tough. LDPE. LDPE's got branch chains, therefore it's amorphous or non-crystalline. It's got low packing density, therefore it's got weaker interchain bonding. That gives it a lower melting point, boiling point, hardness and rigidity, and it can be transparent. And for all these reasons, the fact that it's got lower rigidity and hardness means it can be squeezable, therefore they use it in drink bottles. The fact they can make thin films out of it and it's transparent means used for shopping bags. The fact that it's flexible and electrical insulator means it's used for cable insulation. Two other addition polymers we've got to study. The first one is PVC, or polyvinyl chloride. The monomer is vinyl chloride, or its systematic name is chloroethene, and that's made by reacting chlorine and oxygen with ethene over a copper chloride catalyst. The structure is there, it's got this extra chlorine atom as opposed to ethene having a hydrogen atom there, and when it forms a polyvinyl chloride polymer, that's the structure of the polyvinyl chloride polymer. Every second one on this side is a chlorine atom. It's an insulator, it's tough, it's chemical resistant, such as water, acid and oil. It can be made in two ways. It can be unplasticized. Unplasticized means it's just as is, and these chlorine atoms are quite big, and therefore they make the chain quite stiff because it's hard for the chains to slide past each other. Or you can make it plasticized. You can add chemicals in between the chains to make the chain slide, which makes it more flexible. In the unplasticized form, because it's chemical resistant and because it's quite hard and stiff, it's used for chemical pipes. The plasticized version, because it's chemical resistant, particularly oil resistant, and because it's more flexible, it's used for things like surgeon's gloves. The last polymer we need to study, or the last addition polymer we've got to study in 9.2.1 is polystyrene. Now the monomer for polystyrene is styrene, or the systematic name is ethenylbenzene. It's made by reacting benzene and sulfur with ethene over an aluminium catalyst. Its structure looks like this. It's like an ethene molecule, except it's got a benzene ring rather than one of the hydrogens. Now rather than drawing the full benzene ring, it's sometimes much easier to draw the simplified version. I usually draw this version here, although you can draw it with a circle inside. When you make the polymer, every second hydrogen, or is on this side, has been replaced with a benzene ring. It can be made in two ways as well. Non-expanded. When it's non-expanded, it's hard, it's transparent, electrical insulator, therefore used for battery cases and tool handles. In the expanded form, that means gases bubble through it when it's molten. That gives it low density, it's tough, it's a thermal electrical insulator, therefore used for eskeys, flotation aids, and packaging. And that is the end of that particular focus area. I think our next focus one we're going to look at is going to be AAS and ions.